Hello and welcome to Unit 4, Chemical Equilibrium. We are starting a new unit today. One group will be starting it in class with me and one group is starting it at home by themselves. So you might have seen the video and we've already done the lesson in class, but that's okay. I want to make sure everyone has the information. So Unit 4, Chemical Equilibrium. Just a brief introduction. What does the word equilibrium mean? I think you've heard that equilibrium, that word before equilibrium, usually it means equal, right? Equal, equilibrium. But what is equal for chemical reactions? So some reactions go to completion. We've never actually talked about that, but every single reaction we've ever showed you has gone to completion. It's a one direction arrow. So reactants, products, done. That's the full story. But that's not always true. So we're now going to talk about reactions that can go both ways. It's not always just one direction. Some reactions go to completion. We're not going to talk about the magnesium burning video. So I just said that not all reactions go to completion. So water in a stoppered flask. Oh, I'm going to go get my visual here. So remember back in grade 11 chemistry when we talked about dynamic equilibrium, an open container versus a closed container. In a closed container, the water level will stay at 500 mils. In an open one, it will change. I did that with the grade 11s. This year, remember we did this last year, it started with 100 mils back in February and it's already down to 57. So in an open container, the liquid level drops, but in a closed container, the liquid level should remain at 500 mils. Why? In grade 11 chem, we said, remember the rate of condensation is equal to the rate of evaporation. Both processes are happening here, but this is an unequal rate, so the liquid drops. An equal rate, the volume stays the same. So yes, we are using in grade 12 chemistry what we learned in grade 11 chemistry. So here's our water in a stoppered flask. So like I said, water is evaporating, but it's also condensating. So the reason why this will stay at 500 mils, well, this has been in my room for a long time. The reason why it stays is because, well, first of all, the reaction is reversible, right? There's two things happening. Water first evaporates, condenses, evaporates, condenses, and it's at an equal rate. So we are now using this double arrow. I don't know how well you can see that. When you're in class with me, I'll show you there's a few ways you can draw that double arrow. So it's not always left to right, reactant to products, end of story. It's a little bit more complicated than that. So we did talk about reversible reactions in grade 11 chemistry, but we didn't use any of this language back then. Okay, so water becomes a liquid, it evaporates to become a gas, water vapor, then it condenses back to liquid water, and that is why this should always stay at 500 mils if we don't take the lid off. Okay, so that's kind of the basis of the unit. Equilibrium, when the forward rate of reaction equals the reverse rate of reaction. Yeah, think of this. The forward rate reaction is water is evaporating. The reverse rate, it's condensing. And it's at equilibrium. The volume is not changing. I'll talk about this more when you're with me in class, but we did, this should look similar to the graphs we did in Unit 3, kinetics. You should recognize that this would be the product being formed, reactant using up. So there is some parallels from the Unit 3 to Unit 4. Okay, so that's it for the introduction. When you're with me, we're going to do Lab 9. Lab 9 is a simple lab. You will be making graphs like this and analyzing it. And basically, Lab 9 is the basis for the whole unit. It's a very simple lab, but that, right up in the graphs from Lab 9, that's basically chemical equilibrium in one lab. Okay, so this is the lesson you're doing at home when we're at school doing Lab 9. So we just talked about a reversible reaction. So think of this forward, forward, reverse. So for a reversible reaction, again, we talked about this in the kinetics unit. Capital letters refer to our chemicals, our reactants, our products. So here, capital A and B would be our reactants. Capital C and D would be our products. The lowercase letters are the mole coefficients in front of it. So very simply, the equilibrium constant. We did talk about this last term as well. Remember, we used the letter K for the specific rate constant. In English, the word constant starts with the letter C, but in German and a lot of other languages, remember chemistry, science didn't always start off in English. There's other languages used first. I'll show you later, it's from the German word constant with a K. So that's why we talk about equilibrium constant. We think it should be a C, but universally the word constant doesn't start with the letter C everywhere in the world. So K-E, equilibrium constant, very literal in math and science. So this is how we define the equilibrium constant. So the Ke is products over reactants. Very simple equation. So it should be some pretty easy math for you to do at home on your own. So I know it's a little bit low, but you have the notes at home. So we have two products, C and D are the products, A and B are the reactants. Very simple. It's C And then, so the square bracket, remember those are concentrations of them, are the capital letters. And then the lowercase are just the exponents. So capital C to the power of small c, capital D to the power of small d, capital A to the power of small a, capital B to the power of small b. So again, A, B, C, D aren't actually representing elements in compounds. It's just a generic term. But we will look at real examples with real compounds and elements. But for now, we're just using generic language, so you have the formula that works for all reactions. Okay, I'm skipping over some pictures, but like I said, they'll be easier to explain when you're with me. I just want to give you some explanation with the notes so you're able to complete today's assignment at home on your own. So write the KE expression for the reaction. So here's a real reaction now. 2H2O plus O2 produces 2H2O. So hydrogen and oxygen combine to give water. Well, that's a reversible reaction. You can combine it to give water, but then you can decompose the water to get back the hydrogen and oxygen. So it's a reversible reaction, so that's why we have the double arrow. Again, we just said our formula, KE is reactant over products. We only have one reactant, water, H2O to the power of 2. That was the coefficient. And then we have two reactants, H2 and O2. H2 to the power of 2. O2 is to the power of 1. You could put a 1 there. You don't have to. It's not wrong if you do. It's not wrong if you don't. But if there's no number there, we assume it's 1. So reactants over products. Oh, and that's it. That's how you write. So if I just ask you to write the KE and I don't give you any values, it's that simple. But in your assignment, you're going to do that. Then you're going to be calculating. So how do you actually calculate the KE? So this is the general formula, but we would like to know the actual value. What number is given to the KE? So the actual value of KE can be determined by substituting the concentration of all the substances at equilibrium. So again, to do this properly, you'd have to actually do this experiment. You'd have to do it, and you would do several trials, and you'd collect the concentration of all of these, and then you would substitute and input it. We're not going to do, our lab isn't going to evolve that. So when we do the write-ups, I will always give you the concentration values. Where do they come from? At some point, someone in the world did this experiment and we're using their data to get the values. So that's where those numbers come from. So we're going to use the same reaction. Hydrogen plus oxygen combines to form water, but it's a reversible reaction. That water can decompose back to give you the hydrogen and oxygen. So the equilibrium concentrations for that reaction are as follows. So we'll pretend we did that experiment and we collected the data, and we noticed that when this equation was at equilibrium, hydrogen had a concentration of 0.2 moles per liter, oxygen had a concentration of 0.3 moles per liter, and water had a concentration of 0.1 moles per liter. Now this is an interesting thing to note. At equilibrium doesn't mean they have the same concentration. Equilibrium means the forward rate is equal to the backwards rate. So that's a common misconception. It does not mean that they're all going to be the same concentration at equilibrium. Their rates are equal, not necessarily their concentrations. So just a major concept to keep clear. Okay, so what is the value of KE? So we just did on the other slide, I showed you how to get the KE equation. I think it's a little bit high, but you've got the notes. H2O to the power of 2 over H2 squared over O2. Then, those are the values I told you. I told you at equilibrium, those are their equilibrium concentrations. You are allowed a calculator. This isn't pre-cal math. So you insert, calculate, and hopefully you get the number 0.833. Don't worry too much about sig figs. If we get the concept of KE and getting the values at home on your own, that's great. Now another thing to note is, what's the unit for KE? There is no unit. So KEs do not have a unit with them, just a value. Okay, and then that's it. Okay, so a couple of things to note. So what does that KE value mean? Well, why do we even want to do this in the first place? Why do I care? Why do I need a number for KE? What does that represent? It represents the ratio of products to reactants. The larger the KE value you get, that means a larger amount of product is formed before equilibrium is established. Remember, at equilibrium doesn't mean you have the same amount of product of reactants. The rates are equal. So the larger KE value, if you have a large KE value, that means maybe it's better with the reaction. If you have a large KE value, then it means you're more favored to the right. More products are formed before you hit equilibrium. If you have a small KE value, you're more favored to the left on the reactant side. That's what it tells you about a reaction. I talked about that. Solids are not included. So you will have to look at the states. The states will be given to you. Why don't we include solids in the rate expression? Oh, if we were in class, I would ask someone the answer. Why don't we? Because the concentration of solids don't change all that much. To do this, we're looking for changes in concentration, but when you work with solids, concentrations change so little that it's negligible. So we do not include solids in our KE constants because they don't really affect the overall outcome. So for this case, it would be reactants over products. If we were together in class, we'd do this on the board. So you might think it'd be CaO times CO2 divided by CaCO3, but oh, that's a solid, you don't include it. That's a solid, you don't include it. So that's it. You just include CO2 because the other product is a solid and the one and only reactant is a solid. So watch out for things like that as we go through the unit. I'll remind you of that. And then the third and final, it is dependent on temperature. So I did say Ke is a constant. We know that once you get a constant doesn't change, hence it's a constant. But it's a constant for that certain temperature. If you redo the same experiment but change the temperature, you will get a different Ke value. We'll talk about that again throughout the unit. So temperature changes the Ke value. If it's the same equation, changing the temperature, different Ke. Okay, so the original assignment is a little bit lengthy, so I'm going to fix it up a bit and give you a simpler version that you'd be able to work with at home on your own. So when you're at school with me this week, you were doing Lab 9, and at home you're going to do part of the Ke worksheet. So it should be pretty simple. If you follow the example I did in class, it should work out if you have a calculator. Okay, so good luck with this. Have fun. We are now on Unit 4 of 5.